All right. So hello all. Welcome, I guess, to the first sort of East Coast time zone problem solving session. So the basic plan is that we'll go over some of the exercises or all of the exercises because it was a pretty short worksheet this week. If there's any questions you have from, what happened in lecture or even just stuff that you encountered while you were working on the exercises, we can chat about some of those. And yeah, any other just like miscellaneous course stuff we can chat about too. So feel free to ask questions about whatever, interrupt me whenever, and feel free to send messages to chat if you don't want it, recorded, because we won't be posting the chat logs, but we
No,
will
he
be.
actually did that. What he was doing was the first problem. The first problem said that discuss the foundation and all these problems of this. Yeah, then the lady, I 100% agree. I mean,
Are you intentionally unmuted? Okay. I think that was an accident. All right. Sometimes that's how it is. Okay. So what else? I was going to say something else. Oh, right. If I could just take a quick poll and have people put in chat roughly how they felt the exercises were. Too easy, too hard. This was the first problem set we wrote, so we want to make sure we're keeping it paced to where you guys feel like it should be. Exercise is okay. Pretty good.
Can I ask a question?
Yeah, of course.
So like I watched the first lecture and like when I was watching the Zoom meeting, there was so much movement in the chat, and so I opened the chat like for 5 minutes and then I lost track of everything. I tried to watch the whole lecture again on YouTube, but there is like so much I can't make sense of. So like what should I do?
Yeah, totally. So one, we will never put, okay, I won't promise that, but probably we will never put anything most that like you need to see in the chat. So if the chat is making it hard to follow the lecture, just go ahead and close the chat. You might miss out on some memeing, but you're not going to miss out on any course content if you don't follow the chat. As for the material, well, thankfully you're in like a recitation type section right now, so we can anything that you felt like was confusing from the lecture that you want to go over, I will happily talk about a second time. I will also say the first lecture was sort of about the formalities of homotopy type theory. So, there's natural deduction style proof. As we get further in the course, we are going to start moving away from the formalities, at least during the hot sequence. The AGDA sequence will stick to it a little bit closer. And so if you didn't feel like you understood everything about the first lecture, that is a-okay. That will not harm you for the rest of the class. This was sort of foundational, but it's not going to be the bread and butter of what we study in the class. So
yeah, like my main concern is in just 1.5 hours, there was a lot of jargon and I just didn't know anything. Like, I don't know about other people, maybe they have some idea of what, but I was a bit, yeah.
Totally, yeah. So here, we can keep a list. What are some of the jargon words that you really feel like I can go through a couple if you want. And also
mostly the notation. For example, this that turntable notation, or what was that I copied? Yeah, this notation. Yeah, this notation, like for starting part, I know this meant implication in the lambda calculus, but then after, as we went to the dependent types, I lost track of what this notation means in the dependent type.
Sure, totally. Yeah, absolutely. We can talk about that. The problem sheet was shared in the Discord. Yes, it absolutely was. Although be careful, we changed the link of the problem solving. We changed the link of the worksheet last night while I was asleep. And so I haven't had time to update the YouTube description yet. So, but it's still on Martine's GitHub. So it should be easy to find. And in fact, I should probably pull that up so that we can talk about it. Give me 1 second. Okie doke. Where did you go? So I'll come back. And I can also show you where it is. So here's the HoTTEST Summer School Discord, or not Discord, GitHub. And if you go to the hot, so there's two folders. There's a folder for hot and a folder for Agda. The names are fairly self-explanatory. And in the hot folder, there's worksheets. And in the worksheets folder, there's the worksheet and the solutions. And for the rest of time, this is where the worksheets and solutions are going to live. So I guess let's pull up the blank worksheet first. And then seeing as I'm the one who wrote the solutions, I roughly know how to do the problems. And then again, we will, after we go through some exercises, hopefully going through some exercises will help clarify what these mean. And if we're still unclear about what they mean, we'll hopefully have some time at the end to like go through all of that. Does that sound good to everybody?
Yeah.
Yeah. All right, awesome. Let's do the thing. Okay. So problem one, state the introduction and elimination rules for product types, implications, and pi types. So one. First of all, let's remember what the introduction and elimination rules say and what they let us do, right? I should have chat open. Thank you for setting up. Awesome. Yeah, for sure. Okay. So what do these let us do, right? Well, the introduction rules tell us how am I allowed to build a term of a certain type, right? So for instance, let's start with product rules. Let's say under some assumptions gamma, right? I'm allowed to prove that A has type A, right? This is like a perfectly reasonable thing that you might want to do. And under some assumptions gamma, I'm allowed to prove that B has type B. So yeah, so to go back to this thing about the turnstile, you should think about the turnstile as saying what I am allowed to prove if I make certain assumptions. Okay, so I'm assuming some assumptions in gamma. I don't know what those assumptions are because this is a very flexible framework. And I'm allowed to claim that I have from gamma made a proof of type A. Well, from all of this, this says that, well, if I assume gamma and I can prove A, and I assume gamma and I can prove B, then if I assume gamma, I can prove A and B, right? That's exactly what I assumed. And so this becomes the pair AB. Remember, type theory is what's called proof relevant in the sense that not only have I proven A and B, which Paige was actually calling it in the lectures A and B, but in the worksheet, I called it a product type because that's a little bit closer to not only the homotopy theoretic interpretation, but also the programming interpretation. But you could just as easily call this logical and if you wanted to. And what does a proof of A and B look like? Well, a proof of A and B is a proof of A and a proof of B. So this is saying that if I have a term of type A and a term of type B, then I have a term which is this pair type of type A times B. How do people feel about that? I know I'm sort of saying the same thing a lot of times, but that's because I want to make sure people are following. Okay, we've got a handful of thumbs up. We love it. Where does the term gamma from context come from? I don't know. That's just historical. Assumptions and hypotheses are the same thing. Yep, exactly. Can I expand on the proof relevant aspect? Yeah, totally. So we haven't introduced, oh, there's a hand. Hold your question or send it in chat. Let me answer this other one first, and then we'll get to that. So what is this proof relevant aspect? So the idea of proof relevance is that there might be two different proofs of the same claim. So we haven't introduced disjunction yet, but okay, we have and, obviously we have or as well. So I won't tell you about this yet, but how do you go ahead and show that A and B, so I'll write it down logically, A and B implies A or B. This is obviously true, right? If I know that A and B are true, then I certainly know that A or B is true. And how do I go about proving this? Well, remember in the type theory, we should always have proofs witnessing this. So if I have A and B, I have a proof A witnessing A and a proof B witnessing B, right? So little a, you should think of as being a proof of big A. Okay, well, how do I make a proof of A or B? Well, all I have to do is give you a proof of A or a proof of B. So you can see there's two different ways that I can do this. I can take A and B and get A, and that will be a proof of A or B. Officially, let me write this in like very hard to see font because it doesn't matter. But officially, this is in left of A. But there's another proof of this type. I can take A or B, or A and B, and I can map it to, let me write this in very difficult to see font again, in right of B. And so the idea here is that these are two different proofs that A and B implies A or B. I could either take A and B and just look at A, and that's a proof of A or B, or I can take A and B and get B, and that's a proof of A or B. And that is, these are two genuinely different proofs. And so even though I've proven the same claim, I have multiple proofs of the same claim. And proof relevance is that not only do we keep track of the claims, but we keep track of their proofs as well. So these two things would be different proofs of the claim. Okay. You think that follows from weakening? Oh, I think you're replying to something else. Okay. Can gamma be assumed as a set of variables? Exactly. You want to think about gamma as being not only a set, but a list. So not only, right, it comes in an order. So there's the first element of the context and the second element of the context. And gamma is called the context. Yeah, good question. Is there a reason the rule is not generalized to gamma in the left and delta in the right? So that would make the logic classical. That would be saying that from gamma. So if you have a thing that looks like gamma delta, then that's now saying that I'm allowed to prove anything from delta using gamma. And it turns out that implies law of excluded middle. That's why we don't use that. But yes, if you work classically, that is a different version of natural deduction that you will see. Is A comma B equal to dot BA? Oh, equal dot BA. No, absolutely not. They have different types, so they can't be equal. One of them has type A times B, and one of them has type B times A. And while these types are canonically isomorphic, they are not the same type. Yeah, good question.
So
Okay.
I'm not 100% sure that your answer isn't still relevant, but I think what they meant is like gamma turnstile A and then delta turnstile B.
Oh, are you saying you don't have this? Yes, you
Yes.
will see things like this at some point in your career as a logician. Got it. Yeah, so let me see if I can think of an example. So you might have something that looks like this. You could have, if gamma and A of type, or let's say X of type A, thinks that B has type B. So you should think about this as at the meta level, saying that B is a function depending on X, right? And then if I have an A of type A, then from these, oh, and let's say gamma, sorry, and I have that gamma thinks that A has type A, then from these two assumptions, so if gamma and a term of type A lets me prove B, and gamma lets me prove that there's a term of type A, then obviously gamma proves that B with A substituted in for X. So let me actually be a little bit sloppy with my notation just for simplicity. Let me call this B of X of type B. Obviously, B depends on everything in gamma as well, but I'm just making it clear that it depends on X. And if I sub in A for X, I have a term of type A. Given a term of type A, I know how to build a term of type B. Then B of A has type B. So here are two different contexts, both showing up in the hypotheses of this proof tree. Does that make sense?
And also, I don't want to interrupt again. Oh yeah, go ahead.
Like I was trying to say that maybe one like a clear example will be like a induction, something.
Yeah, exactly. So that's a great point. I don't want to go over induction yet. But okay. On Friday, I think we will be seeing induction on the natural numbers. And you're totally right. I forgot about induction as a thing that exists. And you're right. Induction, we will absolutely be seeing something like this. So yeah, thank you. So you'll see an example on Friday. You didn't get it. How are the contexts different? Because this context is the context gamma and X of type A. And this context is just the context gamma. So those are different contexts.
And then I also think what somebody else commented in the chat about weakening giving you that, I think that was them replying to the person that asked about using gamma for one and delta for the other. Because I think what the idea is what if you had gamma on the left and delta on the right, and then you combined gamma comma delta in the conclusion, really what you could have done in the beginning is just used gamma and delta for both.
Yes,
And just
absolutely.
it would have been overkill. But I think that's why they were saying it. That's what the weakening was related.
Yes, absolutely. And for the logic that we are doing in this class, that is totally acceptable and absolutely works. Depending on if you do other things in the future, like if you learn about this fancy thing called linear logic, you have to be a little bit more careful managing assumptions. But yeah, absolutely. For the purposes of this class, weakening will absolutely allow you to do that. Okay, cool. Good questions already. But let's go ahead and work on these problems. So, but feel free to keep asking questions. I'll just reserve the right for time to not answer some necessarily, or tell you to move them to the Discord or something like that. Okay, so introduction to elimination rules for product types. Well, we've already kind of talked about this, right? If gamma lets me prove, gamma lets me prove that A has type A, and gamma lets me prove that B has type B, then AB should have type, sorry, my tablet handwriting is not good, has type AB. And this is product introduction. So you'll often see this abbreviation, the type that you are introducing, and I stands for introduction. So this is the introduction rule for product types. Then how do I eliminate product types? Well, that tells me how I'm allowed to use them. So if I have a product type, if let's say X has type A times B, then how am I allowed to use X, right? Well, I have two eliminators. Intuitively, you should think that every X comes from a pair like this, right? And so gamma thinks that the left projection, which is PR1 of X, should have type A, and that's one elimination rule. And also, if gamma thinks that X has type A times B, then gamma thinks that the right projection of X has type B. And the computation rules, you should think about PR1 of AB is equal to A. And obviously PR2 of AB is equal to B. Okay. What's an empty context? A context is just, well, a context is a list of variables, and the empty context says there are no variables there. I think this will make more sense when we do a proof tree in problem 2. It's another example of weakenings. Yeah, so an empty context is saying this is true with no assumptions. Exactly, that's another way to think about it.
I'm sorry to interrupt, but like, what do you actually call that turntable thing? For example, above you said it lets you prove this, and like lower in the next part, you called it something else. Like, what is the standard name?
The standard name for what? The standard name for this symbol, the standard name for the line. Got it. So this is called a turnstile. So this is, let me write that down. This is called a turnstile.
No, not the symbol. Like when you say it, what do you say it? Like when you explain it in English?
Yeah, I say gamma proves X has type A times B.
Oh, okay. Thanks.
Yeah. So this is red proves. Different people say different things. Some people just say turnstile. And yeah, but I think of it as gamma proves, or in context gamma, X has type A times B is another thing you'll hear. Yeah, good questions. Yeah, some people just say V dash, which is the LaTeX for it. Is AB just notation for a proof, or does it have pair semantics? It absolutely has pair semantics. That's what these computation rules are telling you. They're telling you that it really does pair and unpair in the way that you expect. Yeah, gamma thinks that is another one that you'll hear.
By the way, I'm not sure what is intended there, but do you mean definitional equality?
Oh, you're so right. I do mean definitional equality. Thank you.
Yeah, I just wanted to make sure.
Yeah, no, absolutely. Thank you. When you do this for a long enough time, you start getting a little bit sloppy with the different.
Yeah, I understand that. And so, there's also so many different notations, like because in HoTTEST you use the 3 bars, and I know that in what is it, Agda, it's like, or wait, I can't remember what it is in Agda.
Yeah, so what it is in Agda depends on exactly which Agda library you're reading, which doesn't help. Yeah, also, thank you, whoever reminded me to enable the live closed captioning. if someone can tell me how to, I'll look into making that automatic because we should make that automatic. Okay, so we have this going on. Okay, so these are the product introduction elimination rules. Let's do functions as well. Let's skip straight to pi types because they're the same thing basically as function types. And that way we can start moving on to building some proof trees. So how do I build pi types? Well, if gamma and the extra assumption that X has type A thinks that B has type B of X. So now the type of B is also allowed. Let me write this as B little b of X has type big B of X. So now this type is allowed to depend on X. So as an example, let's think about maybe gamma and N has type natural proves that let's say the all zeros vector. So the 0 vector of length N has type R to the N. So you can see this is something that's totally true. In fact, we could take this to be the empty context, but let's not for now. So if I have a natural number, then the 0 vector of length N, which is some vector of length N, has type R of R to the N, where now R to the N is some type depending on N as well. Okay, so what's the rule? If gamma and X of type A proves that B of X has type B of X, right? Then gamma proves that, so you can read this as pi X of type A or for all X of type A, depending on the context. But logically, you should think about this as being some kind of souped up universal quantifier. So this is for all X of type A, B of X. And what type does this term have? Wait, sorry. I'm getting ahead of myself. This should say lambda X of type A, B of X. And this has type for all X of type A, B of X. There we go. And so what is this? Well, I know that for every X of type A, I have a term B of X. So this is saying this is a function where if you give me some X of type A, I'll give you the B of X that I promised you exists. And so this is a function which takes an X and spits out a B. Okay. So here X is extra in some sense axiom. Exactly. Yep. Why did I switch to B of X? I switched to B of X to make it explicit that it depends on X. Exactly. Really, this is not just B of X, but the guys in B are also allowed to depend on elements in the rest of gamma. And usually you'll just leave this implicit, but I want to make it very explicit that it depends on X. What is lambda? Lambda is syntax. So in the same way that like colon is just syntax, lambda is syntax. So lambda X of type A, B of X is how you would denote a function that takes in X of type A and spits out B of X. I don't know how this got here, but if somebody could please, I don't know how to erase it either, but if somebody could do that, that would be awesome. I think one of the participants drew it. But okay.
So
yeah,
there was also another good question that maybe got lost a couple.
Sure.
It says something about whenever you do the elimination rules for X, we need to use projections. So should we introduce projections? I think I know the answer, but I wanted to let you say it.
Yeah, totally. Here, I didn't even fully hear where. Oh, so to write down the elimination rules for X, we need to use projections. Should we first introduce projections to do that? So projections are also syntax. We don't need to introduce them. They are just something that exists. And I am, yeah, exactly. So you should think about this term as, you should think about this elimination rule as telling you that PR2 is a thing that exists and that you are allowed to use. Okay, awesome. I think you click on the whiteboard and then clear whiteboard. Okay, thank you. Let me see if I can do that. I don't even know where the whiteboard goes.
It's like done by reactions and everything, probably.
I found myself in some enormous menu. Yeah, I don't know if I have a whiteboard button.
I think you can go to
and
the
it's
view.
wait, clear.
view options
All
and
drawings. Okay, I
annotate.
got it. I got it. Okay, thank you. Okay, so we have this going on. And how do I eliminate? Oops. I should think about this guy here, remember, as being a function, which takes in an x of type A and spits out the b of x that I know exists. Well, how do I eliminate a function type? Well, if gamma thinks that f has type for all x of type A, b of x, and gamma thinks that A has type A, well, I've got a function and I've got something I can apply it to, then gamma thinks that f of A has type B of A. Some things aren't provable in empty context. Exactly. Yep. Some things you need a context to prove. And it's really important to have contexts. Even if you're only interested in stuff that's true in the empty context, you still need more complicated contexts in order to do those proofs, as we are about to see. So let's go ahead and look at number 2. So you can see this proof tree ends in the empty context. So this proof tree says in the empty context, this term, so lambda A goes to lambda B goes to AB, has type, well, it takes in an A and it takes in a B and it spits out a pair AB, right? So let's go ahead and go down here. So in the empty context, I have lambda A of type A, lambda B of type B, AB, right? And what is this? Well, this has type. Let me close this for a second. A goes to B, goes to A times B. And so you should think about this as saying, with no assumptions at all, something is true. And this term here is a proof of that fact. So with no assumptions at all, A and B implies A and B, which is like, okay, we're not exactly doing rocket science here, but it's cool that we're doing like something that is obviously meaningful. And so how do we go about proving this? Well, let's add a layer to our tree. Well, how do I build a term of type lambda A of type A? Well, we just talked about that up here. I build a term of type lambda x of type A blah by having some term here with A in context. So I have an A in context, and that lets me prove lambda B of type B, AB. Oops, sorry, that's bad handwriting. AB. And what type should this have? This should have type B goes to A times B, right? And you can see that going from here to here is an application of the introduction rule for pi types or arrow types. How does the first implied sign is, but the second one is an actual implication? Do you mind rephrasing that? I'm not sure what you mean.
I wanted to say, like you said, A and B implies A cross B. So
yeah, so I'm saying that if you, so yeah, formally, sorry, I guess yeah. So what I'm saying is that if I have a term of type A, so if A is true, that implies that if B is true, that implies A times B.
oh,
Right?
I see. Thank you.
Yeah, totally. Yeah. So the first time I said and, it was like an informal, like we as mathematicians are talking about and. And the second time I said and, I meant like the really precise inside the type theory notion of and. Yeah, sorry, that was confusing. Thank you for asking. Okay, and now I have this, and I have another lambda term. Well, we know exactly how I'm allowed to introduce lambda terms. I now have an A of type A and a B of type B in context. And given an A and a B in context, I need a way to produce AB has type A times B. Okay, well, I also know how to introduce AB of type A times B. If we come up, how do I introduce a term of A times B? Well, I had better have two things. I should know how to make an A, and I should know how to make a B. So let's come over here. So I need to know that given an A and given a B, I should be able to make an A. And given an A and given a B, I should know how to make a B. But this is obviously true, right? These are, if you like, this is variable, or these are just axioms. But if I have an A in context, I'm always allowed to use that A that I have floating around as an assumption. And so this is a proof tree. And you can see how crucial it was. Even though what we're proving at the end of the day is true in the empty context, every other step of the chain used a non-empty context. So even if you're only interested in absolute truths, it's still really important to be able to have these assumptions floating around. Isn't it true that if something's proven given empty context, that the same proof tree works for any context? Yeah, absolutely. So you could replace all of these things. You could carry an extra gamma floating around in all of these contexts. But I'm not for simplicity. But you're totally right that you're allowed to. Okay, does this proof tree make sense? I think that when you see your first proof tree really worked out, I think that that is a point where it starts to click. Is it starting to make sense what happened here? We just used the generic element rule, and now we still need to use the type formation rules? No, so we don't need the type formation rules to finish the tree. The type formation rules are actually a totally second proof tree that tells you that all of these types exist. And we all know these types exist. I'm not going to go over that. So the period before the turnstile represents the empty context. Exactly. So this isn't a period. I guess I think of a period as being down low, whereas this is like a C dot. This is like in the middle of the line. But yes, the dot is telling you that it wasn't a typo. It's not that I forgot to put something before the empty context. I really do mean this to be an empty list. That's all that's saying. That's some notation that you'll see. Some authors don't put anything. Some authors use open and close parentheses. You'll see like a whole bunch of stuff to indicate you want this to be empty. Can I go through the proof tree again? I sure can. Or would you rather go through this proof tree again? Or we're about to do a second proof tree. And yeah, just in the interest of getting through the problem. I know I'm spoiling you all with a second proof tree. In the first line, what is the meaning of the overline? So remember, so you should think about these horizontal lines as saying, if I have this proof and I have this proof, then I'm allowed to say that I have a proof of this as well. And so what I'm saying is, even with no prior proofs, this is always a valid proof. So with no sort of meta-theoretical assumptions, if I have a term of type A in context, I'm allowed to assume there's an A. So you should think about these overlines with nothing on top of the overlines as being like axioms. Some of the other people in the Discord will get mad at me for calling this an axiom, but that's a way to think about it. C dot. Oh, absolutely. Yeah. And same thing, just like I put a C dot here, some authors will put a C dot above this to indicate that they didn't just forget to finish the proof tree. They really did mean nothing else to go on top of there. For some reason, I do put the dot here and I don't put the dot here. I don't know why. It's just how I learned, I guess. These are great questions, great explanations. Thank you.
I have a question.
Mm-hmm.
Why exactly do we need the first line? Because in the second line, we already have A and B in context. Can't we just create A comma B there?
For sure. And the answer is because, so this all has to be super precise, right? And so as a human, I totally agree. We look at this, we say, I have an A and a B in context. Why can't I just make an AB? And the answer is because if you're trying to teach this to a computer, this rule here, this introduction rule, is the only way we have to get an AB. And so I have to use it. I mean, obviously, yes, we as humans can see that if I have an A and a B over here, like just put them in. And yeah, but you need to do this extra step because if you're telling this to a computer, as you all will be in AGDA tomorrow morning, you need this amount of precision is it's just the sad fact of life of what you do. But I agree. From here, it's obvious that the proof works. Yeah, good question.
Thanks.
Would BV-blah say there's a type B, but it's uninhabited? Oh, interesting. So no, so the uninhabited type, there's a thing called zero induction, which is that if you have a term in the empty type, so this is a zero, it's a term, it's a type with zero proofs, then from here, I'm allowed to assume, so it's depending on who you ask, it's called absurd or error or something else, but absurd of X has type A. So this is this is if you like, oh, I forget the fancy Latin for it, but this is the like from false, everything follows. So if you have a term of the empty type, which the empty type is empty, you should never have a term of the empty type, then absurd of X has type A for any A that you like. So in the logic, this is telling you that, yeah, if you like, we can now apply our lambda term to this. And in the empty context, we see that lambda X of type empty proves that absurd of X. And this guy here has type empty goes to A. So you can see that, and you should think about empty as being false. And so this term in your logic proves that false implies everything, because A is a totally free variable here. Yeah, good question. I know that's not exactly what you asked, but I think that's spiritually what you're asking. How we know somehow from outside this tree that A has type. Yeah, exactly. So there's a second proof tree that you would have to build that nobody in practice actually builds that shows you that A times B is a real type. I'm sort of eliding that fact because really the interesting parts of the proof tree builds are these proof terms. And the things that are going to be relevant in our future are the proof terms.
Are you talking about like type formation?
Yeah, exactly. I'm talking about type formation rules.
Yeah.
That's exactly what I'm talking about. Okay, so let's write a proof tree ending with a term of type A times B implies B times A in the empty context. So I want to end with, in the empty context, something has type A times B implies B times A. And normally I would be a little bit coy about trying to figure out what term should go here. But because we're a little bit short on time, I'll just tell you. So this term here, well, it takes in an X of type A times B, right? This guy here should take in an X of type A times B, and I want to spit out a thing of type B times A. Well, what is the only reasonable thing that you could put there? Well, let's pair up the second projection of X and the first projection of X. So we're swapping the order of the projections, right? This is like the only reasonable thing that we could do. And indeed, we can build a proof tree for this really quickly. I guess before we do that, is everybody happy with this notation? And is this starting to make more sense what this proof term is looking like? It's like domain and range. Yeah. Notation is A type and not A type type. Yep, exactly. Very happy. This feels oddly nitpicky, but you'll ask, in all these proof trees, we aren't explicitly stating the judgments like A type. Yes, that is exactly the thing that I was talking about earlier. There is really a second proof tree floating around that shows, it's called a type formation tree, that shows that all of these types really do exist. And I'm not doing that because I'm lazy. But yeah, good question. That is nitpicky, and you're absolutely right. Okay. So how are we going to build this? Well, I want to build some lambda term. Well, the only way we know to do that is to move X of type A times B into the context. And now we want to know that proj2 of X and proj1 of X should have type B times A. Okay, well, I only know one way of building a product type, and that's I need to build something of the left type. So X of type A times B should prove that proj2 of X has type B, and X of type A times B should prove that proj1 of X has type A. Okay, but this is now true, right? This is exactly the elimination rule for products. So this is now, right, let's scroll back up. Where to go? Here we go. So if gamma thinks that X has type A times B, then gamma thinks that proj2 of X has type B. So all we need here is X has type A times B, and that really does prove that X has type A times B. And now I have gamma proves that X has type A times B, and that allows me to derive that gamma thinks that proj2 has type B. And this is obviously true. This is again caching out my context. And we do the same thing over here. If I have X has type A times B, that allows me to prove that X has type A times B. Sorry again that my handwriting is a little bit sloppy, but hopefully hearing me say the words out loud is also sort of helping you follow along. Questions about this? My laptop's about to die. I am listening, but I'm also getting a charger. So what was the question?
Yeah, so I had a question about proving A cross B. So do we have to also prove that A cross B exists? Or
Yes, so absolutely. This is the same. I've answered this question a handful of times, so it's probably worth saying this somewhere explicitly. But yeah, there's a whole second proof tree that you would have to build with type formation rules that show that A times B really is a type in the empty context. And yeah, so I'm not doing that because I'm lazy. But yeah, exactly.
Now that I think about it, was that mentioned in the lecture yesterday?
I don't know that it was.
I don't think it was either, but I'm sure it's in the textbook that they mentioned.
Totally.
And I think the 3 people that have asked that should probably take a look at that because it is pretty straightforward.
Absolutely. Why am I going bottom to top? Great question, because the bottom is what I'm trying to prove. So the way that proof trees work is the stuff at the top are like the assumptions. These are the like global truths that we just assume. And as I move from top to bottom, I am proving more interesting things. And so you start with the thing that you want to prove, right? And then you think, okay, what would need to be true in order for me to assume this? And then you move one layer up the tree. And then you say, okay, well, what would need to be true for me to prove this? And this kind of proof search is sort of exactly how computers do proof search. But yeah, hopefully that makes sense. It's easier to start with what I want to know. And especially for like easier problems like this, there is only one way that you could possibly derive a term of this type. So we know what that has to be. And the proof tree kind of writes itself if you just follow your nose. Whereas if I started up here, right, then now I'm allowed to assume any axioms that I want up at the top of the tree. And there's too much choice there, right? Amazing. Why do we need the topmost layer? Because the only way we have of building proj2x has type B is, where to go? This is the only way we have of showing that proj2x has type B. So we need to make our tree have, in order to get this, we had better have something that looks like this on top of it. And so, so we put something that looks like that on top of it. The lecture had type introduction rules, but we didn't talk a lot about them. Exactly. So I'll stop answering questions about type formation rules, just because, yeah, we've talked a lot about it. And I know I haven't said a lot about it, but I think that's probably a better question for the Discord. But I agree, this looks like it's a point of confusion. So definitely ask about it in the Discord and we can do like a concrete example of it. Okay. So here's this. So problem 4 is what I really wanted to get to. So I want to make sure we talk about it. These are basically like substitution rules that computer follows bottom to top. Exactly. So what is the logical content of these proof trees, right? So we built 2 proof trees, but like, what do they mean? And the whole like power of Curry-Howard is that proof trees turn out to have 2 different meanings depending on who you ask. If you ask a computer scientist what a proof tree means, the computer scientist tells you, oh, that's describing a syntactically correct program in some programming language. And if you ask a logician, which of course, logicians and computer scientists are really the same thing. But if you ask a more dyed-in-the-wool logician, or if you're asking a computer scientist with their logician hat on, what does this proof tree mean? They'll say, oh, well, it's proving some theorem. And we just happen to be keeping track of the proof along the way, right? So anytime you have a proof tree, there's these 2 questions that you should be asking yourself. What is the logical content of this proof tree? Namely, what theorem did I just prove? And what is the computational content of this proof tree? Namely, what program did I just write? And if we look at these, well, what does this do? Well, this is the program. Well, we already know what the logical content is. That's sort of my default language, is to thinking about these things in terms of proof. Love the auto. Oh. Fun fact, I used to be a magician. So people used to make fun of me because I was a logician magician. But okay, so if we have a term of type A and we have a term of type B, then we can build this pair AB. And what is this function? Well, if you're familiar with reading lambda calculus, then you can just read off the function from this. But in something like Python, you might have define, I'm going to leave these things nameless. and this takes in an A. And what does it do? It returns, or I guess I need define. Sorry, I'm not used to having to give these things names. Let's call this out. Let's call this in of B. And what does in B do? It returns the pair AB. And then out returns the function in. So it's a function which takes in an A of type A and returns a function. And what does that function it returns do? Well, that function takes in a thing of type B and spits out AB. And so you can see, right, it's a function that takes in a type A and spits out a function that takes in a B and spits out a pair AB. All right. You ask your logic professor what the proof tree means, I'll say something. Lamau. Yeah, it depends what logic department you go to. Yeah. Anyways. Okay, so this is the computational content of the first proof tree. Let's look at the computational content of the second proof tree. Again, if you're familiar and comfy reading lambda calculus, and if you aren't now, you will be in a few weeks. But if you're comfy reading lambda calculus, this already is a program. But in a more familiar language like Python, what does this do? Define, and this one I really will not give a name. And this takes in an X, right? And what do we do? Well, you should think about this as being return. And now I'm very thankful for Python's very flexible syntax. Let's say this is going to be the pair x1 and x0, right? It takes in an X of type A times B, and it spits out. I know we one index in our syntax and Python 0 indexes. You have to get used to these things, but that's basically what happens. And you can see this is indeed a program that just swaps the input of whatever you give it. How do people feel about this? Does the idea that we are sort of simultaneously writing programs and writing proofs, is that starting to make sense, at least in this kind of simplified context?
I have a question. So the projection 2 and projection 1, are these functions, do we think of them as functions when we're writing proofs?
Yeah, totally. So you absolutely should think about them as functions while you're writing proofs. So this is like a little piece of well, what do I want to call this? This is like this doesn't matter. Okay, but formally this is what's going on, is PR2 by itself does not make sense. PR2 by itself is not something that you can write down. If you write this into your programming language says that syntax doesn't make any sense. However, PR2 of X does make sense, because again, the only way that we're allowed to construct a PR2 is if we're applying it to an X. A naked PR2 doesn't make any sense at all. However, because our logic is expressive enough to allow function types, yeah, okay, PR2 doesn't make sense. But do you know what does make sense? Is lambda X PR2 of X. And so this is a function which takes in an X and returns PR2 of X. And you can see what I'm saying, like, especially if you really have eta reduction in your heart, like this doesn't matter. But formally, if you're trying to be super duper precise about all this stuff, this is very slightly different from just a naked PR2. And this is a real function in your language, whereas this is a piece of syntax without a friend. Okay, yeah, good question. But I agree, that's like incredibly subtle. And so if that doesn't make a lot of sense, you know, what's the David Eisenberg quote? Like, you know, one day when more of the puzzle pieces of mathematics have fallen into place, you can come back to this. Yeah, exactly. I'm not writing the type. We're implicitly assuming X has type A times B. What does it mean that a term records the shape of the proof tree? That is a question for Discord. I don't have time to get into that right now. But the idea is that if you have this proof floating around, then there is a computer program which will take this proof and unravel it and give you the proof tree. So this process that we did of taking the proof and moving backwards and getting the proof tree, that is entirely algorithmic. There's a program that will do that for you. It's called a type checker. And so if you have the proof, then you can unfurl it into a proof tree in exactly this way. If you want to talk about how to do that, now is not the time, but just know that it exists. Was a programmer before you realized you were also a mathematician? Awesome, yeah. Could we bind PR2 to a product type? Regrettably, no. That's a good question, and there are logical systems that let you do that. This is not one of them. Okay. But yeah, so this distinction between PR2 being a function or not being a function is very subtle. And actually, it took me a long time to realize exactly what was happening there. Like a long time. Like I think I was like doing PL theory or type theory for like at least 2 or 3 years before I really realized that a naked PR2 is just syntax. So even if you don't realize, you can still do a lot of really good work, just pretending that PR2 is a function.
I mean, it's probably an artifact too of people being familiar with projections for mathematics.
Yes, absolutely. What does the dot after the lambda really mean? Oh, purely just syntax. This lambda x of type A dot b of x. This is just saying where the input to the function ends and where the output of the function begins. That is all that that dot is doing. Yeah, it means nothing at all. Yep, good question. We do this.
Can I ask a question?
Yeah, of course.
Yeah, so this kind of seems much even more like Python. For example, in Python, you can define inline functions using lambda, and this seems much more like that. This is directly you define lambda. You don't even need to give a name for the function. You say lambda, you define input, and then you tell the how you'll have an output.
Yeah, absolutely. And so these are exactly the same. And that notion of lambda or anonymous function in Python exactly comes from this. And so if you wanted, instead of writing this Python code that I wrote, you could instead write, I think the Python code is FN, is that right? Or no, it's literally lambda spelled out, isn't it?
Yeah, it's literally lambda.
Yeah, so lambda x returns x1, x0. And you can see that this totally valid Python looks exactly, right? Like it's literally the same thing, modulo proj2 and proj1 versus, you know, Python has a little bit of sugar for that with the list indexing notation. And if you were writing Haskell, for instance, then this would literally be what you wrote. Or if you're writing Agda, as indeed we will be in the near future. Okay, yeah, great questions. Okay, wow, I pushed a button, sorry. Okay, so let's, in our last like 5 minutes together, let's try to speed run this swap function, because I know there were a lot of questions in the Discord about why exactly this swap function is definitionally the identity or the
this is what I've been wanting to talk about.
Yeah, so let's go ahead and do it. So first of all, let's just build the swap function. So in the interest of time, I'll just show you the lambda term. So swap AB, well, what should this do? It should have type for all, oh, I forget the order, for all x of type A, okay. So for all x of type A, for all y of type B, I'll give you some c of xy. And I should spit out for all y of type B, for all x of type A, c of xy. So all I'm doing is swapping the order of my arguments. And so we can see what the correct term should be. The term should be, well, lambda f, so I should be taking in some function, and I should be spitting out some function. And what should this function do? Well, it should take in a y, so lambda y, and it should take in an x, lambda x, and it should spit out a proof c of xy. Well, I only have one way of making a c of xy, and that's applying f on x and y. So I spit out f of xy. So this is sigma AB. I know I'm going quickly through this because we don't have a ton of time together, and I don't want to keep you all. I'm happy to go over a little bit because this isn't like for real school, but I don't want to go too far over. CYX in the second one, no, CXY. So CXY is a thing that makes sense. Yeah, C like is a type expecting X as its first argument and Y as its second argument. So we're flipping the order of the inputs, but the type stays the same. That's a little bit subtle. Okay, those subscripts on sigma are kind of a lie because yes, exactly. So CXY, yes, exactly. So these are like A and B that are like fixed for all time. They are, they're not variables. You could make these variables by adding something parameterized on the universe. Where does the F come from? F is a term, I'm not writing the types because the types would take forever, but F is a term of type for all x of type A, for all y of type B, C of x, y. So F is a function which takes in an A and takes in a B and spits out a C of x, y. Yes, you can absolutely see C as being A of type, takes in an A, takes in a B, and spits out a type. Depending on what programming language you use, it won't be called type. In Agda, for instance, we're going to call it U for universe, but yeah, same idea. Okay, so this is our thing, and we want to show, so sigma AB, sorry, let me move this over here. So sigma is going to be definitionally equal to this. And we want to show that sigma composed sigma is definitionally equal to the identity. Or C A times B type. Yeah, same thing. So there's a thing called currying, which will let you go back and forth between those two definitions. Absolutely.
So it might be good to put the subscripts, just saying.
Oh, sure. Yeah, that's probably a good idea.
Just because, I mean, sigma, composed sigma isn't the same, you know.
Yeah, absolutely. Here we go. Okay, and so what are we going to do? Well, sigma BA compose sigma AB, right? So it looks like the main thing that people are struggling with this proof is function extensionality and whether or not we need it here. We don't. But with 1 minute left and the fact that we haven't actually talked about function extensionality in lecture, I'm going to postpone that discussion for the Discord, and I'm just going to show you a computation that shows you that this works. But I agree, the subtlety about function extensionality is good, and we should talk about it. But you know, like Professor Oak, like now is not the time. But please ask in the Discord, and we will absolutely chat about it. Okay, so the idea is sigma BA compose sigma AB, right? Well, we're just going to apply this to some input and like see what happens, right? So, or let's not even apply, sorry, now I'm getting hung up on function extensionality. I shouldn't have even said anything. Okay, let's just do this. So what is the definition of composition, right? I guess we haven't really defined composition, but this is going to be, it takes in an input. So in this case, sigma is expecting an F. Yep. So this is definitionally equal to just the definition of composition, sigma BA applied to sigma AB applied to F, right? And I'm going to now move this over to the left because things are about to start getting long. And people who need to leave, feel free to leave at this point. We're going to be posting this on YouTube. And so you'll be able to watch the last like 5 minutes or however long I go over later. Thanks for sticking around. It's been a lovely first recitation. And yeah, I don't know if I personally will see you all for a while. The TAs are going to be swapping out who teaches these. But at the very least, I'll see you in the Discord. And feel free to drop by my office hours too. Okay. But for those who are sticking around, so this is definitionally what it means to do composition, okay? Well, now let's just expand out these terms. So this is now lambda F, and now this is sigma BA applied to, and now we have to sub in the definition of sigma AB. And sigma AB is lambda F, which I'm gonna call this F1 to distinguish it from the F that we have out here. Lambda Y, lambda X. And then this is F1 of XY, right? This is all I've done is I've subbed in the definition of sigma. And then I want to apply this to F, right? So you can see all that's happened here is I've taken the definition of sigma AB. Let me actually put some parentheses around this F to make it obvious that it's the same. So I've taken this sigma AB and I've plugged in the definition of sigma AB, right? Okay, so now we keep going. So this is now definitionally equal to, now I'm not doing a substitution. Well, okay, I am doing a substitution, but I'm not just substituting definitions. What I'm doing now is application. So this is called beta reduction. And I'm taking this f and I'm taking this lambda term and I'm going to apply this function to this input. And so what does that mean? It says everywhere that I used to see an f1, I substitute in the argument of the lambda term. So this is now lambda f goes to sigma BA of, so everywhere I used to see an f1, I now see an f. So this is now lambda y, lambda x, f of xy. So again, I've plugged in f for f1. Okay. So we go again. Now, this guy here, there's no more reduction I can do to it. So let's expand out sigma BA. This, and I guess I should write down, this is beta, this is substitution. Like I'm literally just substituting a definition. I'm now going to substitute again. So this is now lambda f. And what is sigma BA? Well, sigma BA is going to take in an f2, and it's going to take in an x, or yeah, an x tick and a y tick. Yeah, it's going to take in an x tick and a y, or I guess I should call them x1 and x2 if I'm sticking with the thing. And what am I going to do? I'm going to apply this to f2 of y2 and x1. And so this is, I've substituted in now the definition of sigma BA. And I want to apply this to, oh no, we're gonna have to squeeze a little bit. Put that there. Okay. So all I've done is I've substituted in the definition of sigma BA. And of course, this term here, I don't feel like squeezing it in this corner. But now, what do we do again? Well, I have some function applied to some argument. So we again, this is now by beta reduction. This is lambda f. And now I'm going to, everywhere I used to see f2, I'm going to plug in the argument to my function. So in this case, my argument is this. So this becomes lambda x1 goes to lambda y2 goes to, and now let's plug in f2. So f2 is this, lambda y, lambda x of fxy. So now I've made this substitution. Oh, blue and purple might not be the best for color blindness. I'll double underline this so it's super clear what's happened. Oh, but now that looks like an equality. I'll hash mark underline this. Okay, problem solved. And now we apply this to y2 and y1. Or sorry, x1. Okay, but now, we keep going. Now we have a lambda term applied to some arguments. Well, we beta reduce again. So this is now lambda f goes to lambda x1, lambda y1. And now everywhere we used to see a y, we plug in a y2. Oh, sorry, this should say y2. Why do I have x1, but I have y2?
I wasn't going to say anything. I mean, it really doesn't matter.
It really doesn't matter, but okay, so this was kind of silly naming convention, but whatever. So now we plug in y2 for y, and we get lambda x goes to f of xy2 applied to x1. Oh, there's a thing here. Same with x1. God. Okay, now we're running with it, okay? Everything's fine. Okay, but now again, we have a lambda term in here. So we beta reduce again. We have a function, we have an argument. Let's apply the function to the argument. So by computation, this is definitionally the same thing as lambda x1 goes to lambda y2 goes to, well, now everywhere I used to see an x, let's plug in x1. So this is now f of x1 y2. And now I have lambda f and lambda x1. So now let's eta reduce. Oh, this is beta again. So now I eta reduce, and eta reduction tells me that if I have lambda blah, and then I just plug that blah into a function, that's the same thing as just the function. So eta reduction twice gives me that this is just lambda f f. But this is the identity function. Ta-da! And you can see we never needed function extensionality here. I will say, quick word about it. the reason we have this lambda that we're allowed to cache out, the lambda got introduced in the definition of composition.
Right.
And the lambda gets cached out because the identity function is a function. And so we
Right.
never really applied anything to an argument here. For those of you who are
Lucha,
interested
¿me puede
in this
llamar